Hi there. Thanks for coming back. Um, Now that you've watched a few videos, I'm sure you're familiar with what's shown here. Just a cross-section of a MOSFET, an NMOS to be specific. We have the source here, the gate here, and the drain. And you do know that this is the depletion layer region. And if we give the gate a lot of positive voltage, you know that it's going to become the inversion layer and start conducting a lot of electrons. What we're here to understand in this video and a few more to follow is a few of second order effects that are observed in MOSFETs. What happens is you know how to design, and you get into design and you simulate your design, and you send it to the fabrication department, and a few days later you get back your chip and you try it out and it doesn't work. The reason is you've not accounted for a few second order effects, which are very important, which you might possibly be asked to ignore when you're doing exercises, but when it comes to design, you have to really take care of them. So I'm going to put each of these second order effects in separate videos so that's easy for you to find and brush up on. So this one is going to talk about one very important effect called the body effect. It's also called the back gate effect. What it is when you look at a MOSFET, so it has the source and the drain are reverse biased. You're going to give them positive voltage, and it's connected to N region, so it's reverse biased. So what we have to look at is the fourth terminal. We have three terminals: source, gate, and drain. What about the fourth one? We do have a fourth one called the body, or the bulk, which is called a P substrate. It actually looks like this. It is another terminal altogether called the body, or the bulk, bulk, B-U-L-K, or the body, or the substrate. So even we have to consider the voltage that the bulk has. Generally, because we know that even this has to be reverse biased, for a P plus region, reverse bias would be to connect it to the most negative supply in the system. And you have, say, 0 to 3 volts. 0 to 3. So the most negative is 0 volts. That means, along with the source, even this is considered to be grounded. So in short, the source and the body, or the bulk, need to be at the same voltage. But what if they're not? What if VB, the voltage of the bulk, falls below the voltage of the source? Right? So what happens is this goes lesser and lesser than what it is right now. What happens if the voltage at a P plus region goes lesser than it was before? It'll start to attract more holes towards it, right? Because holes are attracted to negative negative D, so, or negative charge, or negative potential, so they start moving there. But where do these holes come from? They come from here, or anywhere in the circuit, anywhere in the device basically. But what does that mean? When you have holes going towards this terminal, or that region, you're going to be left with more negative ions around here. You're going to have another layer, maybe, of negative ions. In fact, it's a bit more. But in the first place, if you paid attention to the threshold voltage lecture, what happens is these negative ions are here because of VG's positive voltage, correct? The collection of positive charges around this area repels the positive charges from here and leaves us behind with these negative ions. So, and they also have to be in balance. Basically, they have to mirror the charge coming from the gate. For example, if there are a lot of positive charges here, or here, maybe actually exactly, they have to be equal in number to the negative ions. That's called mirroring, right? But now we've not changed Vg, but because of the lowering of voltage at the bulk, we are having an extra layer of negative ions. Now this extra layer of negative ions is going to demand for more positive charges here to be mirrored, to be balanced exactly. Until that balance happens, there can be no conduction. And the point at which conduction starts is called the threshold voltage, right? That means, say our threshold voltage was 0.7 volts. And because of the inclusion of this extra negative ions, it's going to go up to maybe 0.75 or 0.8 volts even. That means you're going to have to waste 0.8 volts of your VG in just trying to start your MOSFET. And that increase in threshold voltage because of the decrease in the bulk voltage is called the body effect. In fact, it's just called the increase in threshold voltage because of changes in the bulk voltage, or the body voltage, or the substrate voltage. So that's about it on the body effect. So it is generally an undesirable effect, because obviously you're going to have to spend more to get the same current. So you have to try to find solutions to how you can decrease that. Of course, we'll discuss that later, but for now you just have to understand that the threshold voltage is increased because of changes at the bulk voltage. Thanks. A few of the other second order effects will follow in the next few lectures. Thank you very much.